Welcome back, everybody. This is our final video for book 3 of chemistry, and so I hope you enjoy it. We're just going to talk about some application of pH and some of the places you might find it in your day-to-day life. So what does it mean to have a shampoo that is pH balanced? Well, the acidity of shampoo does affect hair. Basic shampoos, so that means pH is greater, right? This is pH over 7. Cause the inner shaft of the hair to swell. So if you think about a hair follicle, it's got these sort of uh, kind of things like this on the outside, sort of scales, and that's the hair. But on the inside, there is a shaft of proteins and material, and which can split the outer cuticle. So then the hair will start to split out and separate. Many of the soaps are basic, so washing your hair with just basic regular soap, not like with hand soap, can actually be damaging to your hair. Harsh bases are even used in hair perms, and bleaches and colors are even stronger bases. And so those will dissolve the cuticle, and then they can damage the hair, and they can make your hair feel dull or dry. Meanwhile, acidic shampoos can shrink the inner shaft, causing the cuticle to lie flatter. This restores the hair's original flexibility and shine. And this is why you sometimes need to be investigating different types of shampoos for different types of hair. Now, these are probably generic. I'm not sure if these conclusions about basic hairs, like these basic and acidic shampoos, they might have different effects on different types of hair as well, and different composition of hair from, you know, everybody has a different type of hair for sure, and it will be affected by different shampoos. And so using different types of shampoo for different hair types and finding the shampoo that works best with your hair type is actually a bit of a challenge, so I'm told. The pH of soaps and other cosmetics can also affect your skin cells. The pH of skin is normally around 5 to 6. So basic products can be used to remove skin cells since they dissolve protein, and this will make the skin look brighter and cleaner. But frequent use can also remove too many layers of skin, and too many layers removed can leave the skin feeling, rashed or burned appearing. The top layer also contains natural acids, which protect the skin from infection. So frequent use of basic soaps will remove these acids as that causes a neutralization reaction. Now we also require to think about pH when we think about soil. So sometimes people will add lime to a soil to reduce its acidity. Lime, remember, is one of those hydroxide products. And some crops prefer basic soil, while some prefer a neutral soil, and there are even some that prefer an acidic soil. So for example, legumes prefer basic soil. Those are your beans, your peas, your lentils, while corns and small grains prefer slightly acidic soil, and potatoes and blueberries prefer very acidic soil, like pH less than 5. Soil management is a really important factor in farming and gardening, and it affects the growing conditions for all of your plants. Now, if you're going to be using fertilizer, there is a chance that you could put too much fertilizer down, and this fertilizer would end up becoming a part of the water supply, and this is known as runoff. And so if you use excess fertilizer and other compounds like pesticides and insecticides or pollution from factories and mining and logging, these can all end up in the water supply. So if we think about the natural way of the earth, then you'll have all of the land always descends down towards water. And so your streams and your rivers, they are all lower than the land itself. So if you have a farmland here or you have a factory, right? And what else did we say? Pesticides, insecticides. If you have a mine, I don't know how I'm going to draw a mine, but some here is just a truck of some sort. So all of these things produce runoff, whether it's fertilizer runoff, which is acidic, or if it's pollution, which falls down from the sky, coming out of these things. All of that will run downwards, down the ground and into the water supply. And that water supply can then carry it for far distances, so that places that are downstream of a mine or downstream of a industrial farm or downstream from a factory can end up having their water supplies poisoned. If these chemicals enters lakes and streams, they can change the pH as well, usually acidifying the water, and that directly impacts fish, algae, and bacterial life. They may feed the algae, which can lead to an algal bloom. And an algal bloom is really quite dangerous because those algae are going to use up some of the nutrients in the water and steal those nutrients away from the other organisms and or they can even end up stopping sunlight. They can form sort of an algae crust on the top of the water. So this ends up being algae. And then the sunlight is all being absorbed by the algae and the fish and other things that need a little bit of sunlight, not too much, but they do need some. They don't get what they need, or the plants on the bottom of the water of the lake, they can't get any sunlight, and then they die. And then when the ecosystem is completely put out of whack like that, the whole system can go down, sort of goes down. It no longer functions the way it's supposed to. This may be remediated by using environmentally friendly fertilizers or through the implementation of genetic modification, so that the plants that you're growing don't require fertilizers as much or don't require pesticides. So that's one of the advantages of GMOs, and I don't want to scare you with the idea of GMOs. Genetic modification is typically going to be a situation where we introduce a new protein into an animal or plant. In our case, we've only really commercialized plant modifications, but usually this is this. Well, I'm not even going to get into this. Anyways, typically when we're modifying a plant, we're going to be adding a natural ability, but that natural ability is from a different organism. So typically we have some plant or some animal that has the ability to fight off a pesticide or a disease, or the ability to grow in certain types of soil. Excuse me. And what we do is we move that genetic code over to the plant that can't grow in that type of soil, and then it gains that ability. But it is a natural protein, something that humans and humans and animals have eaten for eons. But it's now in a plant where we normally wouldn't find it. Acid precipitation is a term that we might use as well. So this is another place where acidity is important. So rain and sleet and snow can all form acid solutions and then fall to the ground in lakes. And when that moisture falls to the earth, it can combine with carbon dioxide in the environment, and it can form carbonic acid, which is a weak acid on the ground. So acid precipitation comes from a lot of different sources, but the result is that the water that is normally neutral, like rainwater, will have a pH, and that pH can be as low as 5.3 in some cases. This natural pH level of precipitation forms a weak acid that is considered normal. Okay, wait, I believe I misspoke there. So I see. This first section is about natural acid precipitation. So naturally, water will pick up some carbon dioxide from the air, and that carbon dioxide will make the rainwater a little bit acidic, typically with a 5.3 pH. That's okay. That's considered normal. But when humans get involved, they can lower that pH quite a bit, ranging from 5 to 3, and even in Halifax, they've measured pHs of 1.5. That's the same strength as your stomach acid. And this increases because of sulfuric acid and nitric acid. These stronger and more destructive forms of acid come from pollution. So essentially, sulfuric and nitric acids are created when precipitation falls through an atmospheric blanket of nitrous oxide and sulfur oxide. The water combines with the oxygen in these compounds to form sulfuric acid and nitric acid. So we can write these formulas out. I'm not sure if my Apple Watch is my pen's gonna make it through this, but the water can be added to NO2, and the result is you get HNO3. I believe you need 2 of these, and HNO. And I believe that's 4 oxygens. I think you use 2 of those. Oh no, it's 2 of these, and it's 1 of those. That's 4, 5, 3, 4. Oh, NO2, NO3. Anyways, now I've lost my train of thought. NO3H, NO3H plus. I'll just throw an NO on here. There we go. Okay, there. That will work. So one water can combine with an NO2 and an NO, and that will form HNO3 and HNO. You can also combine them with the SO2 reaction I can do, but we have H2O plus SO2, which gives us H2SO3, which is a type of sulfuric acid. Yeah, and that can also react with oxygen and other things in the environment. So we need to realize that the nitrogen and sulfur oxides have always been present in our atmosphere, but the concentration from natural causes like volcanoes and lightning are very low. Modern industrial processes make use of fossil fuels for production of energy and as part of the refining processes in industry. Consequently, the levels of oxides have risen dramatically in the last century. We now look at oxides of sulfur and nitrogen as pollutants. A pollutant can be described as a substance that is present in a large enough quantity to have adverse effects on animal life. Here are the equations I was looking for. Sulfur dioxide reacts with H2O to form sulfurous acid, and sulfur trioxide reacts with H2O to form sulfuric acid. And that's usually from burning coal. There is discussion sometimes about clean coal, but so far the science on clean coal is pretty poor, or it doesn't have a strong outlook. It would be much better if human beings could move away from using coal altogether and use a cleaner fuel source as opposed to focusing on coal, which we know burns in a non-clean way. And has these sulfur impurities. So coal often contains sulfur. So essentially, burning the coal, you release that sulfur into the environment. You're burning it, so you're burning it by combining the sulfur with oxygen, and that's where the sulfur dioxides and the sulfur trioxides are coming from. Now, nitrogen oxides are also possible. These are coming from internal combustion engines and diesel and gasoline, essentially because these engines are bringing air in, and air is 80% nitrogen. Some of that nitrogen is combining with the oxygen in the hot engines, and that combination is creating these nitrates, and then those nitrates are reacting with the water in the air, and that's forming these nitrous and nitric acid compounds. Over the last 2 decades of the 20th century, Canada has cut its sulfur dioxide emissions by more than half, and the reductions are also underway in the United States. But despite those progresses, however, the recovery of natural ecosystems has been much slower than anticipated. Acid rain continues to affect our lakes, forests, wildlife, and even our health. If you want to see some examples of damage from acid rain, you need only look at at places like Greece. So damage, acid rain damage, and you'll find that there's lots of examples of where acid rain has been damaged. There are things like statues. This pitting that you see in statues like this are due to acid rain. And also in our forests, there are entire forests where the acidity has essentially caused the soil to no longer be suitable for those plants, and also even cause damage to the plants themselves. So these are all places where damage has happened. The more acidic a lake becomes, the fewer species it can support. Plankton and invertebrates are among the first to die, and when they die, they cause a ripple effect. So when the pH of a lake drops below 5, more than 75% of the fish species will disappear. This causes a ripple effect in the food chain and has a significant impact on fish-eating birds such as loons. Not all lakes exposed to acid rain become acidified. Bases found in certain types of rock and soil help neutralize acidity. Unfortunately, most acid rain falls in eastern Canada, where coarsely textured soil and granite bedrock have little ability to neutralize acids. Models predict that even after 2010, obviously need to update this, even after the 2010 emission targets are reached, up to 1/4 of the lakes in eastern Canada will remain chemically damaged. And that is unfortunately the case right now, that we have many lakes, including our own Lake Manitoba and Lake Winnipeg, that are damaged, irreparably damaged, possibly by acid rain. So, this is yet another call for not, not buying a new car, or buying cars that have not taking the car, taking public transportation, all those sorts of things that reduce emissions, and also encouraging your government officials, or your other, your companies that you believe in, or provide, or donating to Greenpeace and things like that, to sort of support the movement towards a greener future, where we don't have as many emissions and we reduce the amount of precipitates, acid precipitates. Forests, of course, so acid rain dissolves nutrients. Acids are typically better at dissolving most things, so nutrients that were in the soil get dissolved. Those helpful minerals in the soil then get washed away before the tree can use them to grow. And they can also release toxic elements like aluminum, which interfere with the uptake of other nutrients. These nutrient-starved trees can experience stunted growth and loss of leaves, and they're more vulnerable to climate stresses and pests and disease. Like lakes, a forest's ability to withstand acid rain depends on the neutralization capacity of its soil, and forests in eastern Canada receive roughly twice the level of acid precipitation they can tolerate without long-term damage. Forests in the coastal and upland areas also experience damage from acid fog. Now, you see a lot of talk about eastern Canada, which is where there's greater industrialization, which means that there's more more pollutions going up into the atmosphere, which causes more acidic rain and acidic precipitation. Now, sulfur dioxide can also contribute to acid rain, and that can react with other chemicals in the air to make tiny sulfate particles, which can lodge in your lungs, cause respiratory problems. And then we have corrosion, which we saw a little bit earlier, that these are the causes of the corrosion of limestone and sandstone and marble. Those are the damage to those statues I showed you earlier. And the acid rain damages the stonework because it dissolves the calcium carbonate, leaving behind crystals in the rock when it evaporates. As the crystals grow, they break apart the stone. So the two oxides that are responsible for acid rain, these are the nitrates and sulfates. Okay, what other forms of acid precipitation exist other than rain? We have sleet, snow, and we also have dry deposition. which I don't remember if we mentioned that. I should have mentioned that earlier. This is when the pollutants land on the ground and then they combine with water afterwards. And so as they combine with the water on the ground, then they become they become the acid components. So dry pollution combines with groundwater. So it sort of becomes acid after it's already precipitated. And with that, we are done chemistry. I will be providing you with some assignments to follow up on this booklet. But other than that, you are finished your chemistry unit, and we'll see you in the next one. Thanks for your attention, and have a great day.